Welcome back, everybody. Okay, so now we want to look at some applications of the fact of the corollary that we mentioned in the last video, that definable sets are preserved under automorphisms. Okay, so that's going to be a way for us to show that some things are not definable. So if something is not definable by automorphisms, then it cannot be definable. So that means that to show that something is not definable, one way to do it is to find an automorphism of a structure that doesn't preserve the sets. I mean, there might be non-definable sets that are preserved under some automorphisms, but not others. There are sets that are preserved under all automorphisms, and still they might not be definable. So this is not an if and only if, but it goes in that way. If you are definable, you must be preserved under automorphisms. So here are some examples. I'm going to leave the first one for you guys to figure it out. The set of positive numbers is not definable in the integers with 0 and plus. We're going to do the next one is a bit more interesting. So let's do the next one and I'll let you guys work on that one. So let's look at that one. Multiplication is not definable in the integers with 0 and plus. How do we show that? Well, if you want to apply the corollary, we need to find an automorphism of the integers, which doesn't preserve multiplication. First of all, let's take a step back. What does it mean that multiplication is not definable? Because we know that what it means for a set not to be definable, but it's an operation. So what we have to do here is define a set that is actually that corresponds to the graph of multiplication. So we are going to consider the set of all triples A, B, and C, which belong to the integers such that A times B equals C. Okay, so this is the graph of multiplication operation. All right, so that's what we mean. That set is the one that is not definable. So how are you going to show that set is not definable? Well, this is the automorphism we're going to take. So let H from Z to Z be the map H of, let's call it Z, equals negative Z. Okay, so actually we saw this in the previous video using actually the reals instead of the integers, but it's not hard to show that this is an automorphism. So H is an automorphism of Z, 0, and plus. Okay, so that means that if M was definable, it should be preserved under H. Alright, so how do we show that something is not preserved under H? So for that we need to find a tuple that belongs to M, and that when we apply H, it stops belonging to M. Or the other way around, which doesn't belong to M and we apply H and it becomes to M. So what is the tuple we're going to choose? Well, consider the tuple, the simplest tuple we can consider, 1, 1, 1. This one belongs to M. Okay? Because 1 times 1 equals 1. But H of 1, H of 1, H of 1, which is equal to negative 1, negative 1, negative 1, does not belong to M, because negative 1 times negative 1 is positive 1. Okay? So multiplication is not preserved when you flip the sign of the integers. So that means that multiplication cannot be defined using just plus. There is no first order formula that you can write using only 0 and plus that is going to define multiplication. Cool. So let's look at the next example, which are actually a bit more interesting. This is the one we mentioned in class the other day. The set that contains only one element, and the element is number 2, is not definable in n times with multiplication. So the set contains a single element, so that means we want a formula that is true only of that element. And we tried a little bit the other day and we couldn't figure it out, and the reason is that no, there isn't any. So we need to find an automorphism of the naturals which maps 2 to something else, so it doesn't preserve 2. Okay, so what is that gonna be? This one is a bit tricky, but it's the naturals only with times. So this is what we're gonna do. So we define the map H from the natural numbers to the natural numbers as follows. So given a number n, decompose it into its prime factors. So for instance, we're going to get that n is going to be equal to 2 to the power of something, let's call k0, times 3 to the power of something, k1, times 5 to the power of something, times so forth, and then we take the lth prime to the power of some number, right? So every natural number can be decomposed into a product of prime numbers, right? So here this is the lth prime number. We're going to define the map to do the following. H of n, what we're going to do is we're going to flip the first two primes. So we're going to take 2 to the k1, 3 to the k0. Okay, so notice here we are flipping. This one goes here and this one goes there. All right, and then we continue with the same number. Then it's 5 to the k2, that stays the same. Then all the other primes stay the same. Okay, so we just look at what is the power of 2, what is exponent of 2, what is exponent of 3, and we flip those two. Okay, so now well, and also we're gonna let, just to be, because 0, I guess we cannot decompose into primes, we're gonna let h of 0 equal 0, it's not an issue. Doesn't affect us. And then we claim that h is an automorphism of n times. Well, I'll let you guys try that out, but essentially, right, if you're multiplying two numbers, when you multiply and you look at the prime decomposition, what you're adding is exponents, right? You're adding the exponents. So if you multiply the numbers and then you flip the exponents of the 203, or if you flip the exponents of the 203 and then you multiply, same thing. Doesn't matter if you flip them before or after. Whatever was in the 2 now becomes in 3. So this operation preserves multiplication, and 2 is not mapped, is not preserved, right? So if you apply h to the set that only contains 2, what you're gonna get the set that contains 3, right? So 2 is not preserved under this automorphism. So try at home to show that this multiplication is preserved. If you don't see that immediately, how will you prove that? Cool. So number 2 is not preserved. So as we saw in class the other day, we can define the prime numbers in this thing. But for instance, 2 is the only even prime number. So if we could define the even sets, then we could define 2, but that means we cannot define the even sets. So this automorphism is quite strange and shows you that a bunch of things are not definable. So let's look now at the third case. That the rationals are not defined within the reals with plus. Okay, and this one is a bit tricky, but it's quite interesting. So the observation is that the reals are a Q vector space. Okay, so they are a vector space over Q. Remember, a vector space is a structure where you can multiply. You can multiply by the elements of Q. This is your field Q, and you can add elements, vectors to each other. But in this case, the vectors are just real numbers. And it's a Q vector space of like infinite dimension, right? And so in a vector space, you have the group structure, you have the 0, and you have the plus, but you have more things, because now you have multiplication by your scalars, which your scalars are the elements from Q, right? So to show that Q is not definable, we need to find automorphism of the group of the reals which doesn't preserve Q, since the Q vector space has more structure than just the 0 and the plus, because it has the 0, the plus, and scalar multiplication. And if you have an automorphism of R as a vector space, in particular, you have an automorphism of R as this, because this is less structure, right? So, but the advantage of looking at the advantage of looking at R as a Q vector space is that we know how it behaves, because when we learn about vector spaces, we know about automorphisms of vector spaces. So all we have to do is choose a basis, pick a basis B for R, and assume that, let's say, the element 1, one of the reals, belongs to the basis. And then remember that from linear algebra, that any permutation of the basis induces an automorphism of the structure, right? Because every element can be written in a unique way as a linear combination of the elements of the basis. So if you permute the basis, you're going to permute the combination, and this is going to give you, so every map from one base to another one is going to give you a map from all the vectors to all the vectors, right? So now consider, so let H be a permutation of B mapping one of R to some other element of the base, which has to be linearly independent with 1, so it has to be non-rational, right? Because all the rationals are the scalar multiples of 1 are exactly all the rational numbers. So if we want to mod, so the other elements of the basis are going to be irrational. And now extend H to a linear automorphism of the reals. Okay, so a linear automorphism means that H preserves 0, H preserves plus, and H preserves scalar multiplication by rational numbers. But we're looking about Q vector space, so scalar multiplication by rational numbers. So in particular, H preserves 0 and H preserves plus, so it is an automorphism as a group. All right, so H is an automorphism as a group, and H maps an H of Q is not going to be Q, because 1, which belongs to the rationals, is being mapped to an irrational, right? So it cannot map Q to Q. It has to map Q to something else. So that's why Q is not definable. Okay, see you guys in the next video.